Hi team, we're going to go ahead and do a practice problem right now that deals with Q equals mCΔT. So that's the relationship between heat and temperature. This particular problem is going to be one that takes a little bit of a real life situation where we might do a little lab type scenario here. And in my situation, in my question that I have for us, we're going to try to find the specific heat capacity of an unknown metal. So in this process, I'm going to have a metal. I'm giving us the mass, so we'd be able to go grab that off of a scale. Here I have the initial temperature of the metal that's going to be put into a calorimeter. So this would be a nice insulated, thermally insulated container here that's not going to allow any energy to get either in or out of the container. We've got some water in here. I've specified that we have 120 milliliters of water. This is the specific heat capacity of water. That's a very easy to look up number. Those units are joule per gram per degree Celsius. I have defined the initial temperature of the water, and then this that I'm showing here is T final. This is a shared final temperature. So go through this thought experiment. We're going to put this hot piece of metal and submerge it in the water. Then we would close this thing up so that the system can come to a thermal equilibrium. And in that process, this temperature is going to go down. It's going to lose some of its heat. And so the temperature is going to go down, and then of course the water temperature is going to go up. This would be a shared final temperature. So in order to do a question like this, I have two separate materials. I've got the metal and I've got water. Both of them are participating in a temperature change. And whenever I have that, so my temperature change is up here, that means that I'm going to be able to relate that through this equation to an amount of energy that's either lost or gained. So I'm going to remove this a little bit. Let's just stop right here for a moment. So I have a Q sub M, that is for metal. And then I have over here a Q sub H2O for the water, obviously, is equal to 0. So what I'm saying when I do this is a little bit of a version of the first law of thermodynamics. This says that energy cannot be created or destroyed. What I'm saying instead is that there's energy that's going to move from the metal, and it's going to move into the water, heating the water up. And the equal 0 part is what allows me to say that this is a closed system. No extra heat comes in, no heat is lost to the surroundings there. I put some signs up here. It's important to remember that the Q equal mCΔT, the signs are really important. If you lose energy, you're going to be a minus sign. Gaining energy is a plus sign here. And so I've indicated the signs that I'm expecting out of these. Those signs mathematically come out of the final minus initial of the temperature. Okay, so the next step, once I feel good about this setup, the energy lost is going to be shifted over here, and that same quantity is gained. I'm going to write a Q equal mCΔT equation here for both of those different substances. So now I'm swapping out, instead of Q, I'm going to write mCΔT, and it's for the metal. So mass of the metal, heat capacity of the metal. I should have said specific heat capacity of the metal. Delta T of the metal. And then I'm going to add to it a new fresh Q equal mCΔT, but this time it's for the water. Mass of water, specific heat capacity of the water, delta T of the water. If I come up here for just a moment and I point out all the units, as long as I stay in the units that I have shown up here, I have unit agreement. And so you're going to notice that I have most of those things already in line. If I come over here for a moment, I have a volume of water. I'm going to need to convert that volume of water to grams, and I'll do that in a little bit. But I'm going to probably not show a full cancellation of all my units in here because I'm doing a pre-check to make sure I have the units that I need to be in to have my unit agreement. All right, let me move this up a little bit. I'm just trying to create a little bit more room here. Let's go ahead and start plugging in our numbers. So to begin with, let's do the mass over here of the metal. So I'm going to go ahead and say 68 grams. That's the mass of the metal. Here's the C for the variable that I'm actually trying to solve for. Delta T is always final minus initial. And so final is 32 degrees C minus the initial temperature was 96 degrees minus 96 degrees C. Okay, that is going to collapse down, and that is going to be a minus 64 degrees Celsius for me. Okay, but let's go back up here and add. Now we need the mass of water. I'm not going to show the work for this. I bet you've probably done this before. The density of water is 1 gram per milliliter. And so I have a very straightforward conversion here where I'm going to say 120 milliliters is actually going to be the same as 120 grams. That's assuming, of course, the 1 gram per milliliter density of water. So I'm going to go in here and I'm going to say 120. I'll put a dot. I'm showing a third sig fig that way. Gram of water, okay, times the specific heat capacity of water, 4.18 joule per gram per degree C. And then I'm going to have my delta T of the water here. And so my final temperature is here. My initial temperature is there. So 32 degrees C minus 21 degrees C is equal to 0. Okay, again, that was the first law of thermodynamics argument. This, of course, is going to collapse down to 11 degrees C. Energy increase, temperature increase, this one, of course, dropped. All right, so now let's go ahead and simplify this down a little bit. I'm going to combine the 68 and this information. So let's do minus 64 times 68. Okay, I'm going to have negative 435. I'll round that to 1, so I'll hold 4 sig figs, even though those probably aren't all legitimate. I'm kind of dropping my units. Again, remember that I had unit agreement up here, and so I'm going to be pretty confident in my final answer here. Okay, so there's this term. And then I'm going to add to it, let's multiply these 3 numbers together. 11 times 120 times 4.18. So plus 5518. You can see that I rounded that just a little bit as well, is equal to 0. Okay, let's go ahead and put this term on the other side, making both of my terms positive. And then let's go ahead and divide through by this guy so that I'm isolating for C. So if I show that over here, I would have 5518 divided by 4351 is equal to C. And so I'm going to take that original number divided by 4351. And now I have C, which is my specific heat capacity, is equal to 1.268. Let's stop it there for a little bit. Let's talk about our significant figures. So if I come up here and let's look at this number. Now I held 4 sig figs when I combined this down, but it looks like I have 3 sig figs, 3 sig figs, 2 sig figs in the 11. So this is actually only good to 2 sig figs here. Okay. Over here, I have 2 sig figs and I have 2 sig figs. So this is going to be good to 2 sig figs also. So I had 2 sig figs of kind of reliability divided by 2 sig figs. I should probably only report 2 sig figs here. So 1.3, and because I'm pretty confident in my unit agreement, I'll come up here and grab the appropriate units of joule per gram per degree Celsius. Okay, so there's my 2 sig fig final answer. Hopefully that was useful to you.